I think it's quite interesting to compare these different examples of dipolar, if I could use that word, boson systems and or dipolar interacting quantum particles. I'm going to try and, for this diverse audience, say some things that will hopefully make it clearer how these quantum Hall dipolar condensates are similar and how they're different to the other ones we've been talking about yesterday. I won't talk too much about actual research work, maybe now and again during my talk. And where I do, it's work done by Fengcheng Wu, who's now a postdoc at Argonne National Laboratory. Fei Zhu, who is sitting here, will be presenting a poster today that I'll mention briefly as I go along. And Ming Ji, who's, I may mention some of his work at the end of my talk. So there's a reference that if you're interested in this from 20,000 feet point of view, that you can read. I wrote together with Jim Eisenstein now quite a while ago. I don't agree with everything that we wrote then, but mostly I agree with what we wrote. Yeah. So much of what I'll say is connected to ideas that are explained in that perspective article. Okay, so mostly I'm interested in dipolar condensates in the quantum Hall regime. I'll explain exactly what I mean by that. But Bose condensation, usually we understand as in terms of macroscopic occupation of a single wave function, which is allowed for bosons, as Leonid was explaining yesterday. Or if we think about a boson system or a part of a boson system where particles can be exchanged with an environment, then the property is that every time you add a particle or every time you remove a particle, it's got the same phase. So this, if you think about this particle annihilation operator in our normal Fock space treatment of Bose condensates, the expectation value of this is non-zero. And this requires, of course, breaking a symmetry in a certain sense, although a very famous physicist you all know by the name of Tony Leggett hates talking about this as a broken symmetry, but I'm okay with it. The broken symmetry is particle number. There's coherence between states with different numbers of particles. Okay? And that's, for what I'm going to talk about, that's that symmetry. And the fact, which is connected, of course, with the fact that particle number is normally conserved in many particle systems, is a good way of thinking about some of the ideas that I'll mention. Okay? So there's one important difference between bosonic atoms or molecules and effective bosons inside a solid-state system. That is, an atom's a boson until you rip an electron off or rip a proton out of the nucleus, whereas usually the bound states that are important for Bose condensates inside a solid crystal are much more fragile. And of course, bosons, electrons, we're talking here all about electronic states, and electrons are fermions, so bosons have to be made out of pairs of fermions. And the most perhaps spectacular type of boson in a solid state system is a Cooper pair, which is a pair of electrons. And Cooper pairs Bose condense in superconductors. But it doesn't take too much energy typically to rip a Cooper pair apart to get into this higher energy scale where the Cooper pairs are not bound together. In fact, often we can't completely avoid it. So this pair condensate inside a crystal has that type of distinction that is often relevant to observed properties and different from the real bosonic atom system. And there's another important difference. I'm not, in fact, talking about electron-electron pairs in a superconductor. Electron-electron pairs in a superconductor have to do with, with particle number because they're electrons, pairs of electrons. And you can, of course, take a pair of electrons and put it in the Fermi sea, if you like. So sometimes it's only the parity of the number of electrons. That's a good quantum number. But in any event, there's a broken symmetry in a superconductor associated with particle number conservation of the underlying many electron Hamiltonian. The exciton condensates always, and dipolar exciton condensates in particular, are a different type of fermion pair that acts like a boson. They're particle-hole pairs. And the most, particle-hole pairs are different from particle-particle pairs in a number of different ways that are important. First of all, they're not charged, so they don't couple to electromagnetic fields in the same way. But also, you can ask what symmetry is broken. If I have a condensate, which means I have an amplitude for making these particle-hole pairs, and the indices here is that it's a pair formed by making a hole, and I just put here, to give the common example, V for valence band, a hole in the valence band, and an electron in the conduction band. What kind of, if that amplitude is not zero, what kind of symmetry is that breaking? And typically, in fact, this is an issue, and it's not, there's no exact symmetry that it's breaking, but that's, and so you have to take account when you talk about particular observations of the fact that that this amplitude often couples to some real term in the Hamiltonian. The condensate couples to something, unlike a superconductor. Okay? So particle-hole pair numbers are typically not perfectly conserved, and that has important consequences, some of which have big experimental manifestations that I won't actually talk about. Okay, so in the case of, I'm borrowing your language, Ronan, and I will use it forevermore in referring to these as dipolar exciton condensates, but we've used various other words, as I was chatting with Leonid about yesterday, over the history of this subject. And very often people will say, instead of dipolar condensate, spatially indirect condensate. So this is a condensate that people couldn't imagine back in the day, and it's a particle-hole pair where the particle and the hole are in separate layers in space, and that gives you an opportunity to really conserve as very accurately that particle number, so you can more closely approach the limit in which this really is a broken symmetry. And so the condensates we're talking about are systems where spontaneously, due to electron-electron interaction effects, there is an amplitude for making a particle-hole pair where there's a missing electron from some group of states in one layer and an added electron in some other group of states located in some other layer. And so there's coherence then macroscopically between these two different layers, even though there are no terms in the Hamiltonian that actually impose a phase for that or actually can move particles from layer to layer. So dipolar, this is a long-winded way of saying, one of the words you can use, and one of the words we sometimes use to describe these states, are they're states with spontaneous interlayer phase coherence. And that's often the best way to look at these states. Okay? Yep.
Regarding the slide before about the nature of the pair.
Yeah. I can't imagine that.
The Cooper pair itself, if I imagine the state, this multi-electron state, is actually that every electron do not only have one partner, let's say when they are in the BCS regime, but actually coupled with many, and that they are all coupled. And so now, with the Exciton pair, should I imagine that one electron is coupled to one order, or that, let's say, it's simultaneously coupled with many orders?
So it's more like a superconductor, but you're asking a microscopic question, really. And you're describing the mean field theory of superconductivity, which is, of course, a very good theory. And, but what's really, most essential, independent of these microscopic aspects, which are also important, is that this amplitude is non-zero. Or in the exciton condensate, I have a broken symmetry state where this amplitude is non-zero. In the microscopic theory of this that I'll sort of slide by you, indeed, it's more like a superconductor where the field, if you like, that drives the formation of this condensate involves all of the electrons in the system. Okay. Okay, so I'm going to say a few things in the context of yesterday, mostly about what's different in the quantum Hall system. And one of the things that's different compared to the spatially indirect condensates that Leonid and Ronan discussed yesterday is these are equilibrium states. They're not pumped steady states. They're electron-hole pairs in equilibrium that have spontaneous phase coherence. And the most studied experimental case until recently is this case is actually the most studied equilibrium dipolar exciton condensate occurs in the quantum Hall regime. And what it really is you have, as schematically indicated in this cartoon, you can easily make systems with two quantum wells where some electrons are stuck in one quantum well, some are stuck in the other quantum well, and electrostatics plays a dominant role in determining how many are in one layer and how many are in the other. And in the quantum Hall regime, that I'm going to say what's special in just a moment, the case where this state has been seen is where in both layers, all of the electrons are in the lowest kinetic energy Landau level. Okay, so a particular group of states in a two-dimensional layer, the number of states in a Landau level is equal to the number of flux quanta that go through the two-dimensional electron system, so you can easily adjust it experimentally. And these spontaneous phase coherent states, or dipolar exciton condensate states, are most robust when, if you choose to describe these two sets of Landau levels associated with different layers in a particle-hole language by doing a particle-hole transformation for one of the two layers. They're most robust when the number of electrons in one layer is equal to the number of holes in the Landau level in the other layer. And that means that actually that the sum of the number of states that are present in the two layers is enough to fill one Landau level. Okay, so in the quantum Hall jargon, it's filling factor 1. That's where this state is most robust. But it does occur at other filling factors as well. Okay, so their equilibrium, I'm claiming that we know very well that this spontaneous phase coherent state occurs in the quantum Hall regime in double quantum wells at Landau level, filling factor equal 1. Now I'm going to make a few remarks about that are kind of theoretical remarks, and that is that this particular physical system has some remarkable simplifications. And that makes it possible to do some theoretical calculations almost analytically that might be more difficult in outside of the quantum Hall regime. And it's actually helpful in thinking about these ordered states to broaden your perspective and think not only about the case where I have, the case I was talking about, whereas I have a lowest kinetic energy Landau level in one layer and one in another layer, and they're almost degenerate. There are electrons in both. But you can generalize that idea to any case where you happen to have two Landau levels that are nearly degenerate. And we know that when you have two or more Landau levels that are nearly degenerate, and you have enough electrons only to fill up one of the Landau levels, then you almost always get some kind of broken symmetry state. And these states are often described using a sort of block sphere language where you form a block sphere out of whatever the two Landau levels are that are crossing, apples and oranges, for example. And what happens, at least this exact statement in mean field theory, what happens is that the electrons occupy all of the orbital states available for one of the two Landau levels, and they choose the Landau level they occupy out of this twofold block sphere Hilbert space to minimize the energy. Okay?
What are the two Landau levels?
So for a bilayer, it's Landau level in one layer, Landau level in another layer. But there are many other examples that we know. In every case, there's a broken symmetry. Okay? So one of the other examples, perhaps the earliest one that people started to think about and was discussed already in a very early quantum Hall paper by Bert Halpern at a conference I was actually at in Switzerland, and published in Helvetica Physica Acta. This is the most highly cited paper in Helvetica Physica Acta. And he made a number of interesting remarks there connected with the theory of the fractional quantum Hall effect. But I'm not going to go through this argument, but related to the way we understand Laughlin states and some of the other incompressible states that occur in the fractional quantum Hall effect, there's the following statement. Let's imagine I have two Landau levels, and what he was thinking about there is a single kinetic energy but two spin states. Okay, so instead of two layers, a spin degree of freedom, and I have enough electrons to fill up one Landau level. The conclusion was the ground state. This system is ferromagnetic, even without any Zeeman coupling. The electronic ground state is spin polarized. And how do we know that rather rigorously? You know, normally, if we try and do a many-body theory and say whether a system is magnetic, it's a strong coupling phase transition, and it's hard to do anything rigorous, but here you can. And the reason is that if you look in the Hilbert space of electrons that have minimum quantized kinetic energy, it turns out that there's only one state in that Hilbert space which has the maximum total spin quantum number, which is fully spin polarized, has total spin quantum number n over 2. It's actually this state, which is many of you will recognize as a van der Waals determinant. It's a totally antisymmetric wave function. And of course, then it has to be multiplied by a totally symmetric many-body spin wave function, which is the all spins aligned wave function. And so the upshot of this is we know rigorously, in this case, that the ground state chooses to occupy one Landau level, that it's ferromagnetic. So it turns out that this proof relies on spin rotation, the spin independence of the Hamiltonian, of the interaction Hamiltonian in this case. In the bilayer, of course, we have electrons in two different layers, and the way they interact depends whether they're in the same layer or in opposite layers. And so we don't have total spin as a good quantum number, but this observation gives us a rather rigorous way to do theory with a small parameter being the separation between the two layers. Okay? So, but the brief summary is we really know that these states break symmetries. And how do they break symmetries? This is a paper I wrote with Thomas Jungwirth a number of years ago. And basically, these systems can be either, in magnetism jargon, either Ising magnets or XY magnets, or in special case of spin, where the Hamiltonian is really invariant under, independent of the Landau level orbital label, it can be Heisenberg in form. And I'll come back to this later on at the end of my talk when I talk about very recent experiments on bilayer graphene systems. But let me just say briefly that it turns out so easy plane, broken symmetry in this case, means I want to be phase coherent combination of the two starting Landau levels. In the case of a bilayer, I have electrons, Coulomb interaction doesn't want me to change, electrostatics doesn't want you to change the density in the individual layers. So the only way to form an ordered state is to establish phase coherence between them. So generally, when the two crossing Landau levels are in different layers, you get easy plane type of quantum Hall ferromagnetism, which is exactly the same as saying an exciton condensate, okay? Whereas when the crossing Landau levels are in the same plane and they're different in some way, for example, maybe they have a different kinetic energy, then you want to make an Ising magnet. That means you don't want coherence. You want to stay either in one of the Landau levels or the other. Okay. Okay. So I'll come back to that. Okay. So there's actually, this is one of these subjects that has a theory prehistory, before any experiments. It's an example. When my experimental colleagues tell me you guys are just doing crazy stuff, that will never be relevant. Okay, so there was a bunch of theory work on dipolar exciton condensates in the quantum Hall regime before there were any experiments. Of course, usually when theory goes ahead without experiment, many things are wrong. I'll give you an example now. Okay, so this is the mean field theory for two crossing Landau levels with minimum kinetic energy, one in one layer, one in the other layer. You obviously can experimentally easily make them cross by just applying gate voltages. The important parameter here is how far are the layers apart, that's D here, compared to a characteristic length scale L, which is a magnetic length. It's basically a length scale associated with the area that contains one flux quantum. Okay, and so this is an important point here, that usually the dipoles that are involved in these solid state dipolar condensates are not point dipoles. That's true, of course, in the atomic case as well, but they're very nearly point dipoles. Here they're very much not point dipoles. And this layer separation compared to sort of size of the electron, which is what you can think of the magnetic length as, is sort of a measure of how dipolar they are. Okay. When the layers are close together, there's the state that at the time in this paper we called uniform coherent. I don't even remember what DWS stood for, but it's exactly the same state we're now calling a dipolar condensate. It's a state with spontaneous phase coherence between the two layers.
Allan, what is the y-axis in this stuff?
So the y-axis is energy of competing states. Okay, and so this is energy. When the layers are close together, the lowest energy state is this broken symmetry state with spontaneous coherence between the layers, the dipolar exciton condensate. When the layers are far apart, then we know, very well from our experience in the quantum Hall effect that this mean field theory calculation gets the wrong answer, because mean field theory says that when you have electrons, when they're very far apart, of course, the two layers are isolated. Each layer is half filled. And mean field theory says the electron state in that case is a Wigner crystal. Okay? But we know it's not. There are some quantum fluid states that mean field theory doesn't know anything about. So what happens in this mean field theory calculation is you have a condensate, and then for small layer separations, for large layer separations, you have Wigner crystal in each layer. Okay? In between, you have both the broken translational symmetry of the Wigner crystal, and you still have coherence. Okay? So this is actually a supersolid state, according to and that's what mean field theory predicts in this case. But we know from many experiments that I'll be talking about in a minute, that's not what actually happens. What actually happens is that when the layers are close together, we get this state. But then there's a first order phase transition at some layer separation to a state that has no interlayer phase coherence and has so a strongly correlated state within a fractionally filled Landau level, usually called a Wigner composite fermion state nowadays. Okay. Any questions? So yeah, go ahead.
So if you think about this supersolidity in terms of Exciton, so Exciton should be characterized by some dispersion in plane.
Yeah.
What do we know about the effective mass? Is it parabolic? Do you have Rotten minimum? Usually for a supersolid, you should have a Rotten distribution.
Yeah, I'll come back to some of that at the end, depending how far I get along. But in fact, connected to these properties I mentioned at the beginning about simple, we can actually nearly exactly calculate the collective mode spectrum. Yeah. Okay. Okay. So my next part. Yeah. Go ahead.
Maybe you're going to talk about this, but maybe it's related to Alexis' question. So usually when we think about a gas or a weakly interacting or strongly interacting, doesn't really matter. You start with some sort of a parabolic dispersion for the particles.
Yes.
And then when you have a condensate, the dispersion changes. You get a Bugle dispersion. You get collective excitation.
Oh, you're talking about well.
Just
Well, you're conflating the dispersion of the charged quasi-particles and the neutral collective modes in that discussion. But in any event.
So what I'm trying to ask is, in here, when you start with particles that have a very different dispersion, they're
dispersionless.
Yeah.
So from the beginning, interactions are something's going to happen.
Right.
Right. And
so I'm just thinking of how should I think about this condensation. Is it more? I mean, in some sense, it's different than when you start with something that has quadratic dispersion, right?
Yeah,
Because
not very.
kinetic energy here.
It's a microscopic detail, and it's a relevant microscopic detail. But yeah, it doesn't really. The collective mode dispersion is the same. Yeah, it's linear dispersion. Yeah.
Question. I mean, when you talk about a condensate, then there is a critical temperature.
Yes.
Which you get condensation.
Yes.
What is this temperature for you?
So there'll be costless-Thales phase transition, and in this system we can estimate it rather accurately. It's around 1 degree Kelvin or something in gallium arsenide.
For that, you also have to assume that there is a particle with some dispersion radiation, right?
No, I mean a simple.
You have to talk about the Pauli wavelength of some object here.
You can if you wish.
So on.
You can if you wish. That's the starting point for weakly interacting particles, right? And we can do all that here.
Okay.
Yeah. Maybe
But if it's a flat, I mean, degenerate Landau level.
yeah. That's the charged quasi-particle dispersion. The neutral excitations have quadratic dispersion. Actually, have linear dispersion. Yeah. I'll come back to that. But all of that language you're using there is the language of weakly interacting bosons. And here we can get further than that often. But actually what we'll do at the end is I'll talk about something similar to weakly interacting bosons. I probably won't actually, but yeah, go ahead. Maybe during the coffee break. Go ahead.
So then, okay, you're right. We are always in mind with weakly interacting phase.
Yeah.
Our system, then let's go to the strongly interacting regime. So for me, it's interesting to understand what is about quantum diffusion condensate, or what is about that it's similar to helium. Helium is strong, very strong interacting. Let's say Exciton
Y- Yeah. So if I want to use that language here, then I can just tell you the answer. I can't explain the answer. But as I said, what actually happens in this system is that there's a first order phase transition at as you control the tuning parameter of the interactions. The depletion, the condensate is about 50% depleted, and then there's a first order phase transition to a different state. Okay? So something very different from helium. It's actually kind of amazing that helium gets to 8% and doesn't make a phase transition to some kind of different state. Yeah, anyway, all these comparisons I think are quite interesting. But let me go on and talk about some of the phenomena. So I chose this word here from, advisedly, I took it from a paper, okay? The paper is the first paper, as far as I know, that talks about this idea that excitons can condense in a crystal. It's written by a fellow by the name of Blatt, who was at NYU. I talked about this at NYU not so long ago. Nobody knew Mr. Blatt. I think he left a couple of years after he wrote this paper. Obviously, actually, I should ask the people at UNSW. That's one of my places I stop regularly. So apparently he went there. Okay. So what he said, what Mr. Blatt said, was, if this ever happened, you certainly wouldn't see it in any spectacular electrical effect. And that sentence here that I took from his paper is where I took the word spectacular, because I think one of the most interesting things about this type of condensate is, indeed, the way you see it, most interestingly, is spectacular electrical effects. Okay? And this is one of the spectacular electrical effects. And indeed, if I get toward the end of my talk, I'll show you recent drag experiments. This is a standard way of looking for an equilibrium dipolar condensate. What it is I have two different layers. They're completely electrically isolated. Just trust me that you can do that experimentally. And you drive a current across one of the layers, and you measure a voltage in the other layer. If you have a magnetic field, you might measure a Hall voltage as well. And so this is actually a standard way of, a standard type of experiment. And usually, if you have a Fermi liquid state, a ordinary conductor in one layer, it's actually not a uniform fluid, has a little bit of quantum fluctuations. That creates a little friction with the other layer. And you can measure a very small voltage in the other layer. When you have a bilayer exciton condensate, when you have spontaneous phase coherence between the layers, the quasi-particles that carry current through this system actually are a coherent combination of both layers. They don't know which layer they're in. So as soon as you form this state, you measure the same voltages always in both layers. Okay? So even though this is completely disconnected electrically, but you measure the same voltage you measure in this layer. Okay. Now I'm just going to mention this quickly. It's not going to be relevant to anything I say, but it's definitely very relevant when you think about doing analogs of these experiments in zero magnetic field exciton condensates. And that is the fact that quantum Hall systems, it turns out, there always are edge states, even when you have a gap in the middle. And that's important for some details of these transport experiments that I'm not going to emphasize. Okay. Okay. So let me mention an idea, which is the way you understand these transport experiments, essential idea for understanding these transport experiments. I should have mentioned at the beginning, so this particle hole, this state is a particle hole condensate that doesn't break translational symmetry. The other example we know is a ferromagnet, and there are many analogies between this phenomena and phenomena that occur in some magnetic systems, including the following one. So charges are carried through this system by the quasiparticles. The quasiparticles interact with this condensate. The quasiparticles are changed, just like they are in a superconductor, for example, where the quasiparticle Hamiltonian, because of its interactions with the condensate, has particle creation terms and particle annihilation terms. In these bilayer condensates here, I've just written this down schematically. This stands for some interaction between a density in the top layer and a density in the bottom layer. And when I have coherence between the layers, I can replace one of these particle hole, pairs of these particle hole amplitudes associated with different layers have a non-zero expectation value that they fluctuate around. And therefore, what happens is this interaction, what happens is the quasiparticles, due to their interaction with this condensate, it produces an effectively large, a huge tunneling from one layer to the other. And that's another way of thinking about the statement I made a moment ago that the electrons don't know which layer they're in. Okay, so the quasiparticles think there's a huge tunneling amplitude between the layers, even though there's none. And but nevertheless, it is true to good approximation that microscopically electrons can't tunnel from layer to layer, so you have to conserve particles in both layers. And the way that happens is, let's say, for example, in an experiment like this, as described in more detail in this paper, if I have a quasiparticle coming into a region where I have a condensate, it sees, due to its interaction with the condensate, it thinks there's a big tunneling amplitude to get to the other layer. So it's immediately reflected and to the other layer. And if I wire it up like this, then the way it can get from source to drain is by coming in, scattering off the condensate, getting to the bottom layer, and then this area is gapped, so it can't go through there. So then it goes around external current loop and can tunnel back and exit. Okay, and but every time it does that, it has to make an exciton. Every time an quasiparticle comes in and tunnels between the layers, it makes an exciton, in order to conserve charge between the two layers. So that when in this steady state of this circuit, what happens is charges are moving like this, but that drives an exciton current, electron current in this direction, hole current in that direction, and to complete the circuit. Okay. This is basically, the most interesting experiments or most extensive experimentation in this area has been done by Klaus von Klitzing in Stuttgart and by Jim Eisenstein at Caltech. This is a recent experiment from Jim from a couple of years ago that shows this effect. To avoid the edge states, he actually makes these electron rings, and he drives a current across the top layer in this insulating state. And if there's no wire connecting inside and outside on bottom, then basically there's some huge resistance and no current can flow. But if he allows current to flow this way, then what happens is it drives the current on the outside, and magically a current appears in this loop where there's no driving current, which is just closing the whole part of the excitons in the other layer. Okay? So there are spectacular electrical effects, and I can't my friends at UNSW and in Australia made this lovely video, and so I got to show it. Oh, I should have.
The second fleet theme will use exciton superfluids. In an exciton transistor, two layers of semiconductor are used. One layer contains electrons, the other holes, which are missing electrons and act as positively charged particles. The negatively charged electrons and the positively charged holes attract each other and bind together to form an exciton. Collections of excitons condense into a superfluid, which can flow without resistance. This superfluid can carry electrical currents in opposite directions in top and bottom layer.
Okay, that's just what I said, but with a beautiful voice. Go ahead. Yes, so I was going to say two things about this. One thing that I won't emphasize is that the dissipation associated with superflow, nobody's been able to measure it yet, so it's immeasurably small, but as you know, two-dimensional superfluids always have a finite resistance, so there presumably is some resistance. And the second point I was going to mention is the one that Leonid alertly noticed, that this system is wired up differently than the one I just showed you. And indeed, the way the exciton currents are closed is by applying a loop at this end. And what that means here is that there's a voltage drop along this wire because there's current flowing along it. So that means the electrons, the local chemical potential in this wire at the top is different from the bottom. So this is actually, in this case, it's actually a dynamic. It's not an equilibrium exciton condensate. It's a dynamic exciton condensate. The phase coherence between top and bottom in this experiment has not been measured, as Leonid would emphasize, but it has to be time dependent. And this is electrically generated, but it's more or less the type of condensate that people make by pumping with light. And indeed, it's never been done, but if you made this resistance so that this time dependence was in a frequency range where you had a detector and allowed for just a little bit of leakage between the layers, which you can easily do, then you could see light coming out from this. And so somebody should do that, Ronan. And the thing I want to emphasize is, to the extent that these optically pumped condensates really have long-range phase coherence, they're just like this. The only difference is the phase between top and bottom has the time dependence, and the time dependence is what I always refer to as the chemical potential of the exciton condensate. Okay. What was I going to say next? Okay. So my last, go ahead.
Just one question. So, is it possible to have a case where so if you're in a filling factor 1/2 in each of the layers, if you do have, due to the Coulomb interaction, you would have formation of electron hole pairs, but without phase coherence. So a state where you do have exciton, but not exciton condensate. Or they always come, or are they always come together?
I think, so you're asking what happens. We know what happens to your kind of system when you go to high temperature. You still have excitons, but they're not coherent. Right. What would happen here when we go to higher temperature? I think you probably actually have a first-order phase transition to some quite different kind of state.
And that is because of this dispersion is different? Because there's no...
It's due to the difference in the microscopic physics, this is really, and the answer, I'm going to show you something connected to exciton density later, and my answer might be exciton density dependent. But this is really high exciton density, right? Like, it's commonly said, as Leonid mentioned yesterday, that if I have a high exciton density, I'll have a Mott transition. I don't think anybody really knows that for sure, but this is the regime we're in. And because of the quantum Hall of physics, we don't have a Mott transition at low temperature, but I think we would have some kind of transition to a state where you don't have bound electron holes at higher temperature.
So in this case, you always have the pair formation and the coherence. They always show up together.
Nobody's actually measured the coherence, although let me go back.
Allan,
Yep.
if you look at the Kalin and alkaline theory, where you create an electron hole, when you excite an electron from a field level to a higher level, you do have an electron pair, an electron hole pair, which has a dispersion.
Yeah, that's what I've been saying.
This is what I'm answering to. I mean,
But
I mean,
but
it's not
that's
that you
that's
don't
different
have in
from.
this system electron hole pair that disperse and you do.
Yeah, you're talking about, and I'll come back to this later. You're talking about a case where you have a nearly filled Landau level and a nearly empty Landau level. Okay.
I'm not talking
And-
about
But
this particular one.
but this is not the case where you get the superfluidity.
No, but I'm saying that in a quantum Hall system, if I'm not sure I got your question right.
L-
In a quantum Hall system, it's not good to say that you cannot have the analog of an exciton, electron hole pair, which has a dispersion, unless you have a condensate. That is not the case.
Yeah, so we have one exciton states, but we're really talking about this many exciton case. Anyway, so I think, everything that's been said is true, including by Israel. Okay. Okay, so I want to end off in the last 10 minutes or so. I'm actually taking, you're the chair, right? So, no, you're the one of the organizers, so you interrupted me, so I'm taking the time back. No, okay. No, I'll stop. Okay, so this is a recent experiment. There are two different labs that have very similar results. Philip Kim's lab at Harvard and Corey Dean's lab at Columbia. These are all drag measurements. As I mentioned before, that's the standard way of just measuring something convenient to say that you have spontaneous coherence between the layers. And it's a double bilayer graphene. So it's a two-dimensional material. Graphene has its own peculiarities in its Landau level, and that gives them an opportunity here to explore some things that are related to some of the ideas that were mentioned yesterday. So it turns out the n equals 0, the Landau level, I think you all know about graphene, Dirac points, and so on. And it turns out that because of the details of bilayer graphene, there's a Landau level that's at the Fermi level of neutral bilayer graphene. And there are two different states with cyclotron orbits, quantized cyclotron orbits of two different sizes that happen to be degenerate. Okay? And what this is, it turns out that when you include the spin degree of freedom that the electrons in graphene have and the valley degree of freedom, it turns out there are two places in momentum space that states can exist. That when you fill up the Fermi level of graphene, then you do it, let me go across here. This is indicated here by the blue and red. This is filling up this Landau level that's right at the Fermi level when the graphene is neutral, or nearly neutral in a magnetic field. And this is filling up, the blue ones are you're occupying an orbital that is the same as the one I've been talking about in gallium arsenide. It's a minimum quantized kinetic energy of a certain size. And then it turns out, strangely, that the red ones, then you're filling up an orbital that has a bigger cyclotron orbit radius, okay, with a little quantum wiggle in it. It's actually the same wave function that in gallium arsenide has the next highest quantized kinetic energy. Okay? So that's filling up these n equals 0, n equal 1, 0, 1, 0, 1 in one bilayer, and this is doing the same thing in the other bilayer. And so people know, understand from many other experiments exactly what's going on here. And so in these various boxes here, each Landau level, 1, 2, 3, 4, so this is 8 by 8. There are 64 boxes here. And in these 64 boxes, what people are doing experimentally is with gates, they're moving one Landau level across another. Landau levels localized in one system, separated by an insulator hexagonal boron nitride, moving it energetically across another. Okay? And sometimes the Landau levels that are degenerate are both n equals 0. When I say n equals 0, that means the Landau levels I've been talking about in gallium arsenide so far. And sometimes the Landau levels that are crossing are blue. Sometimes they're red. And blue and red are different. Maybe that's the most important thing. And, and actually, blue is even, red is odd, as I'll mention in a moment. And one of the things that you see here is, whenever you see color, that means they see a big drag voltage. They see the same voltage, same Hall voltage in one layer as in the other. And I'm not sure how well you can see this here, but this is, for example, two crossing Landau levels that are each half filled, and if I go diagonally across one of these blocks, the sum of the filling factors of the two Landau levels is equal to 1. That's the case I've been talking about. And you notice that this big drag doesn't exist just there. And that's something we know, I just haven't been talking about it. But you can go all the way from the regime where both Landau levels are half filled to the regime, where down in one of these corners, one of the Landau levels would be filled and the other one would be nearly empty. That's the kind of limit that Israel was talking about. And right. So you can get coherence all over the place, but you only get coherence when both of the Landau levels have n equals 0. Okay? So why is this? I'm going to skip this. Okay. This is actually a plot of the energy. This is, you can call this exciton-exciton interactions. It's the energy associated with exciton density fluctuations in the system. And I haven't shown you how this is calculated, but I'm going to say a few words about what ingredients enter this curve. One thing is we can calculate this exactly. This is this energy of fluctuations as a function of the wave vector of those fluctuations. And there are several ingredients that enter this. One is electrostatic interactions that are, let's say, the dipole interactions. And in addition, there are exchange and correlation effects, actually only exchange effects in this mean field calculation. And if you go to very rapidly fluctuating in space, large wave vector fluctuations, it always costs energy. And that's really associated with what drives the stability of these states, which is exchange interactions between the two layers, which you can only have if you have coherence between the layers, and you lose that when you when it fluctuates. if you go down here at small wave vector, let me just concentrate on this. You can see here that the energy of fluctuations is decreasing. This is actually Q equals 0, the beginning of this curve. And initially, it decreases linearly. This is the long-range dipole interaction, which makes the Fourier transform singular, and it gives this dominant behavior that Luis, I think, was, or several people discussed yesterday. And the electrostatic interactions help stabilize this state, but you quickly lose that with wave vector, and this mode, nearly completely goes soft. You can calculate the energy associated with density fluctuations and phase fluctuations, and the collective mode energies are, since density and phase are canonically conjugate, are just the geometric mean of those. I just haven't shown you the phase part of it. And this is stuff that Ming-Ji has been looking at more closely recently. If you look at, this is a case for coherence between a 0 Landau level and a 1 Landau level. And you can see here that when the layers are close together, as they are in bilayer graphene, the energy associated with fluctuations is, even long wave fluctuations, is negative. This state is not stable. It's not a surprise that they didn't see spontaneous coherence when 0 and 1 were degenerate. And that's really the point that Thomas Jungwirth and I made a number of years ago, that when you, these states will be Ising type ferromagnets. They don't want to form a state with coherence. They want to stay with one orbital character or the other. They don't want to form coherence between them. And, and this is the case where both Landau levels have index 1. And you can see it's kind of close. Let me make a remark. You can see that this is this dipolar effect as the layers get further apart, which makes the energy go down very, very quickly for layers that are farther apart with wave vector due to the long range of the Coulomb interaction. I guess this is the so-and-so instability, 2D version of it. And it becomes negative here. And why is this happening? According to these calculations, actually, if the layers are close enough together, this state can be stable. We'll see whether future experiments agree with that. But what's really going on here is that the wave function, the Coulomb repulsion energy here is not point dipole repulsion. These orbitals have a size, and the excitons, if you like, have a size. And in this case, where they're n equal 1 orbitals, they have a little wiggle, a quantum wiggle in their form factor, if you like. And it turns out that this form factor for interactions between these electrons in this Landau level actually ends up exactly vanishing around this momentum. And so somehow the Coulomb energy, which is stabilizing these states, can be completely eliminated. And so I think this is kind of interesting connection between this and the atom case, because it should be possible in further experiments to explore the region where this instability occurs closely, and unless it's preempted by first order phase transition. Okay, so I'm not going to discuss this because my time's up. I don't want to give the chairman a hard time, but I just want to say that this is a continuation of our conversation yesterday, Ronan and Leonid, and I want to continue at the coffee break. Okay. So okay, let me stop. Okay, thank you.